Good afternoon, ladies and gentlemen. A fabulous time here in Miami, beautiful weather. I've had some wonderful talks already. I'm here to talk about something that is really near and dear to my heart, and that's basically how do we help people in the industry to understand cybersecurity and safety analysis. And what I'm trying to do is bring forward concepts from my previous experience working as a control system designer at Ontario Power Generation to get us all off the hamster wheel of pain. And so why did I come up with this concept called the information harm triangle, right? And what does it mean? Well, when I started at Sandia, I became very, very interested in the use of systems theoretic process analysis. And this is a systems engineering approach and hazards methodology that was developed in response to the Challenger accident and Dr. Nancy Levinson, MIT. And the key part of this is essentially you have things that go wrong within your system, and this results in an unsafe control action. Those UCAs are the things that we are trying to prevent. And why do we try to prevent those unsafe control actions? Well, because if you have an unsafe control action, that's going to bring about a hazard, and a hazard will bring about a loss. And so a really simple example would be, a traffic light, right? A traffic light, one light's green, one light's red. Well, the unsafe control action would turn both lights to green. And that brings a hazard, right? A hazard that two drivers going the opposite directions could actually cause a vehicle accident that would lead to a loss of vehicle damage, injury, or loss of life. And so STPA maps unsafe control actions to those consequences that we're trying to avoid. The second part of it is in cybersecurity, we've already focused on integrity and availability and confidentiality. And this actually came from basically J.P. Anderson's study within the Air Force in the 1970s that said, how do we stop harm to our information? And that's sort of a real key part that I sort of internalized and said, why are we so focused on integrity and availability of the information in the digital world when we should be more worried about what does the harm to the data provide the adversary? And so the information harm triangle tries to bring in both these concepts so that you do protect your integrity, you do want your digital information to be accurate and complete, you do protect the availability product, but you turn the challenge of this really ambiguous way of adversaries attacking our OT systems and you turn it into an engineering challenge. And so how do we take this approach and use it to understand how adversaries can interact with the systems to bring about those physical losses, right? In our community, we care about those things that harm people, persons, the environment, society, and property. And so how do we understand how the adversaries can enable that and reduce that to basically build out protections in defense in depth to limit their harm in the digital space and limit the harm within the physical world? And so what is the information harm triangle? Well, the information harm triangle starts with data, right? So one of the things that's really interesting is that, as a control system designer, the control systems, they don't act directly with the digital world, right? You have analog to digital converters, you have digital to analog converters, and what they're really doing is they're taking a snapshot and they're producing a digital representation of what they believe is occurring within those physical processes. So it's no different than if you were to take a photo of me and then add a mustache, right? You're not really impacting the physical world. And so this is really important to understand that data can only be interpreted by digital systems. That's the first practical postulate. There's 4 of them for the information harm triangle. Now, postulate is not a truth. It's a practical assumption you take to simplify the approach of the analysis techniques. The second one is that cyber attacks can only affect the data, right? Cyber attacks can only increase digital harm, and this allows you to divide and conquer that engineering analysis that I'll show on the next slide. The third practical postulate is that the physical consequences, the one we care about because we want to protect the environment, safeguard people and property, those are the ones that are only produced by physical harm, right? That's that physical information harm. And the final postulate is that in order for an adversary to result in physical harm from a cyber attack, they need to have a transform function, and that's where the unsafe control action comes in. So as you notice, both data harm and physical information harm, they're orthogonal. And this really provides tremendous insights for how you can build in defense in depth and how you can accredit tasks and activities for safety within your security analysis. And so how do we simplify this approach into an engineered analysis? So as I mentioned, you had that first postulate was data can only be interpreted and used by digital systems. We as humans can't use data. Right? We don't understand it. I can't tell whether it's a 1 or a 0 by touching the line on the wire. And then the second postulate comes in, and that's what you're seeing here, is you have a cyber attack can only increase data harm. Right? And so this cyber attack, it adds a plus to the data harm, and eventually the adversary is able to cause enough data harm to initiate that unsafe control action and start that cascade from the unsafe control hazard to bring apart the hazard that brings apart the physical loss, that consequence. So it's no different than that traffic light example, right? You turn both lights to green, eventually you wait long enough, you're probably going to get a car accident, and you might get definitely vehicle damage or injury or death. Now, how do we stop that? Well, one of the ways is you can look, how do I limit the data harm? Right? These are your intrusion detection, protection systems, your firewalls, your antivirus. These are the things that interact directly with your data, right? Just like digital systems, you need digital systems to protect those digital systems from data harm. But what we've found as well is that you also have measures to reduce physical information harm. And these are like mechanical interlocks, they're governors, they're even gears, right? So as an adversary, if I'm doing a cyber attack, I can't change the volume of my pressure vessel. I can't change the size of a pipe, or I can't affect a physical lock. And so by having these together, we actually take this from a really unambiguous situation into an optimization problem. And a lot of my team have really benefited from this concept when they sit and they say, as an engineer, I'm trying to limit the data harm and initiate a UCA that brings about large amounts of physical information harm. And so we've done a lot of testing that I'll describe in the future slides. But first, I'm going to come up with a simple example. I'm a nuclear system designer, and so I'm going to talk about a pressurized water reactor. So this is a simple light water reactor, pressurized water reactor, and one of the key safety functions, one of the primary safety functions is remove decay heat from the core. And so what you're seeing here, there's 3 thermodynamic loops. The red is the primary loop, and this is the one that transports the decay heat, that heat from fission, from the reactor vessel, and transfers it, conducts it to the steam generator, which provides the heat source for the secondary loop, which is in purple, right? And so the purple then is high-quality steam that creates the energy you need to drive the turbine, the steam turbine, and then it basically vents out that heat to the atmosphere through the condenser. And then finally, you have that tertiary loop that provides for cooling water for the condenser. So in this way, you have a transporting of heat through the 3 loops from the reactor vessel on the left to the condenser on the right, which is actually the ultimate heat sink of the environment. So one of the key safety events that could occur, this is not from cyber, is something called a steam generator tube rupture, right? And this is where you have a break in the steam generator tubes that will result in the loss of primary coolant, which is light water, from the red primary loop. Right? And so this is going to cause all kinds of bad things. And so there's usually an automatic decision made by the main steam isolation valve. That's the MSIV. And so the adversary is able to notice that there's been a steam generator tube rupture, and they're able to prevent the main steam isolation valve from closing. Now what this means is you have now condensate ingressing into that secondary loop. And with that condensate, you have the potential for damage to major equipment like the turbine. So you definitely want to prevent this. So anyways, the unsafe control action would also result in things that would become apparent to the operator. And so what you're going to see is you've got this light water. Light water is a wonderful neutron absorber. And what's going to happen is when it's ingressing into the secondary loop, you're going to get radiation fields outside of containment. That's what that symbol is right there. You've got these radiation fields. And that's a really bad day, so that's going to create a big alarm, right? The operator is going to see that alarm, and they're going to go, I think I have a steam generator tube rupture. But this is such a significant event, there's also other things that would alarm, such as you're losing mass. You're losing mass, you're losing that water from the primary loop, so now your flow is going to start to decrease, and you would start to have an alarm on a flow mismatch, right? You're expecting X amount of flow, and you're getting less than X. And so that's the second alarm. And then the third one, because the primary loop is a closed system, but that rupture actually makes it now open, you're going to see a pressure decrease. So now you have 3 alarms. And so what this means is that if the main steam isolation valve fails and you see that unsafe control action, the operator is going to intervene. And how does that look with the information harm triangle? Well, how that looks is we have essentially the operator action is going to see those 3 alarms, right? The radiation in the outside of containment, they're going to see the steam generator flow rate mismatch, and they're going to see the pressurizer decrease. And they're going to basically intervene. They're going to say, oh, I know what the problem is, and I'm going to close that isolation valve and protect the turbine and stop the egress of that radiation into the secondary side. But what happens if the adversary says, hey, I'm going to inhibit, I'm going to hide those alarms from the operator? That means we can't really accredit for the operator to perform the action in order to limit the physical harm at the necessary physical information harm limit, which is shown in the red dotted line. But we have 3 alarms, right? And this is sort of where we got into a lot of our experimentation. The operator is likely going to make the same decision if they have 2 out of 3. It's a simple voting system, right? If they see like the radiation alarm or the pressurizer decrease, they're probably going to continue to say, oh, this is a steam generator tube rupture, and make the right decision. What happens if they only have 1 of the 3, right? It's likely they'll still be conservative and do the correct action, but it's not guaranteed. And if they spoof all 3, then that unsafe control action of leaving the isolation valve open will remain. And so that's sort of what you're seeing with these 3 different information harm triangles, is that A is where you say you spoof the radiation alarm, B is where you spoof the radiation alarm plus the flow mismatch, and then C is where you inhibit all 3 of those alarms. And so right away we start to realize that the operator has a cap of how much data harm they can withstand and still be able to meet the requirements of protecting that physical information harm. And so this is why it's so critical when we design our measures to say, hey, I can lose 1, but I can't lose more than 1. And so then how do I build and design my systems, especially with my intrusion detection, to say, hey, adversary is able to inhibit 1 alarm, now we need to put additional effort, apply additional resources to really know when the adversary is inhibiting 2 or 3. And that's how you get to lower the data harm limit to an amount that only the information harm triangle that represents scenario A, which is that single alarm inhibited, is actually allowed. So this is tremendously important for how we do our defense in depth. And so how did we validate this? Well, we've been really lucky. The reason why we're really lucky is because at the International Atomic Energy Agency, we have the SHIRA pressurized water reactor. And there's some in the room right here that were really involved in developing that pressurized water reactor. And this example, we call it the SHIRA pressurized water reactor, has all the components in that previous conceptual example. It's got the primary loop, has the pressurizer, has the steam generator, and then it has the turbine and the condenser. So we're able to actually use real physics models, right, and simulators, and we plug those in to something developed at Sandia, what we call the emulation platform. We actually have a name for it called Arcade. Our focus is on advanced reactors, and it's called Advanced Reactors, Cyber Assurance, and Development Environment. And so right now it only works for the Ashira model, but the goal of our work with this network emulation is to have true plug-and-play functionality. That people that have MATLAB and Simulink type models can provide them to us, and we can plug them into the network emulation and run these recursive and automatic tests that I'll be describing in the next experiment scenario. So what do we want to do with this approach? Well, one of the things that's really, really important that we really feel strongly about is that a single UCA, just like in the previous example, will not really bring about the large, severe consequences that we really need to be focused on. And so we were looking at how do we see combinations, right, of a UCA on the reactor coolant pump, and then we sequence that and time it correctly with the reactor, with the steam generator. And so one of the things we really found with this experiment was that we wanted to take the reactor coolant pump flow down to 0, and then second, we wanted to freeze the steam generator throttle so that it would take the pressure down to 0, right? And we were trying to say, you know, are there sort of resonant effects, right? Is there sort of a standoff timing where basically we create unstable states within the overall nuclear power plant that result in more significant impacts than we'd expect? And sure enough, we did. We created open source automatic tools what's called manipulate process I/O, and we were able to essentially automate these tests and just stand off the timing between those UCAs. So in this example, that UCA1, which is that reactor coolant pump, we basically set the set point and we get the flow to end. We started that at 500 seconds. And it took 1,300 seconds to take it down to 0. Right? Pretty bad day. You're not so good. You're losing that primary coolant. Essentially, you're no longer transferring heat from the core to those steam generators. Right? But then we looked at the steam generator. And we said, hey, what happens if we have a UCA on the steam generator to take the pressure to 0? And this is the maximum harm example. At 1,400 seconds, that's 900 seconds after the first UCA on that reactor coolant pump, we actually initiate the second one. And one of the things that's really, really important is that the second steam generator UCA results in rapid depressurization. And you'll see this in the information harm triangle on the next slide. But the one thing that we didn't expect is the DNBR ratio. And people that aren't nuclear engineers won't understand what that is, so I'll explain it. DNBR is the departure from the nucleate boiling ratio. Okay? So what this is, it's just like when you jump in a pool, right? You jump in a pool, and it's all water, and it really cools you down a lot faster than the atmosphere. Well, the DNBR basically represents when a steam jacket forms across the fuel and prevents the liquid water from coming into contact. So you're no longer able to conduct heat and transfer it from the fuel rods to that. Now, when the DNBR is flat, like you're seeing before those two UCRs, there's no rate of change, you do not have that steam jacket forming. You do not have the fuel being insulated by those steam jackets. But when the DNBR, the departure nucleate boiling ratio, starts to increase its rate, that is when you see that steam jacket forming, and that's when the fuel starts to heat up. And the most severe consequences in nuclear power plants today is when you have fuel melt. So if you're not able to reestablish that cooling, the fuel will continue to heat up and you'll get fuel melt, which is a really, really bad day. And so how does the information harm triangle look at this? Well, we have UCA1, that's that reactor coolant pump, right? The data harm is the same because it's a set point attack. So the data harm is the same between the UCAs, we did the same thing. But the rate of harm for the reactor coolant pump, it took 1,300 seconds. 1,300 seconds to set it to 0. With the steam generator, it took 400. So there's the rapid depressurization, so the rate of physical harm from UCA2 is much higher. So what do you think we would want to really protect against, UCA1 or UCA2? Well, our way of looking at this is UCA2, the steam generator, the one that brings rapid change through the unsafe control action to hazards to loss, would be what you would prioritize your resource to protect against. And so it's no different than the traffic light example I talked about at the beginning. Right? I talked about a traffic light example. We have the two both ways showing green. If you're up north in the Arctic in Canada or Finland, right, there's no cars there. You could leave both green lights on all the time. But if you're in downtown Miami, it won't take long for that hazard to bring about the loss. And that's what we're seeing between the reactor coolant pump and the steam generator in this example. Now, the question we have, because of this sort of resonance type effect where the sum is not equal to the parts, so UCA1 and UCA2 separated by 1,300 seconds is literally going to bring about more harm, and that's shown in the departure of nucleate boiling ratio. So how do we bring those into summing up, right? Summing up these information harm triangles so we can get a composite UCA1 and 2. What does that mean? And so what are our future efforts for rigor? We want to look at how do we investigate data units and physical information harm. So with the reactor coolant pump, we had kilograms per second. For the steam generators, we had pressurizers, right? So we had pascals. Those things don't relate correctly. But there is one concept, there's one property that is in both data and control systems, and that's entropy. So we're doing a really large effort to discover what are the linkages between entropy, between data and physical information harm that could apply and normalize these approaches. We also looked at cumulative harm and rates of harm. So our initial research, as shown in the last one with the reactor coolant pump and the steam generator, does point to that this is rates of harm, which actually was a really interesting finding because I based this concept off of an engineering concept called the power triangle, which is watts, which is joules per second. So it seems sort of coincidental, at least initially, that it's a rate-based calculation. We also looked at the effects of timing and sequencing. So how do resonance come into this? How do the sum of UCA1 and UCA2 get represented? And then finally, we really want to basically apply formal methods and rigor. We want to adapt this into control theory so that first year, second year engineering students can learn how to do these combined safety and security analysis. And so finally, this is a new approach for defense in depth, right? Right away in the first example, we were like, you can lose one of the 3 alarms. So if you've got to protect your data harm, you've got to be able to detect when you're losing one alarm and then prevent any further data harm. In the RCP and steam generators, it shows you what to prioritize, those UCAs that bring across quick changes between UCAs, hazard, and losses. We also want to combine safety and security analysis. We don't actually provide the STPA analysis. We go out to advanced reactors at Sandia, and they provide us with their STPA analysis, and then we adopt this concept. We adapt it for their needs. We also built out advanced modeling and simulation tools. That's Ashira is from the IEA, but we want to build the network emulation platform, and we want to have it plug and play. So if we can have more models, make it more versatile and interoperable, that benefits our community writ large. And then finally, the biggest thing I always had is when I was at the IEA, there was a conference, and somebody stood up and said, you have 10 cybersecurity experts do the same risk assessment, and you get 10 different results. And so my huge goal with the information harm triangle is that we could get a 3rd or 4th year engineering student to have the same information harm triangles that a 20 or 30 year professional, to bring that repeatable and consistent analytical approach that can give us sort of the single source of truth for our community and get us off that hamster wheel of pain. So thank you again for your attention. I'm here for questions. So please, if you do ask a question, come to the microphone. Thank you very much.
I was just curious if any of this is written up in a white paper or anything at this point, if I want to dig into it a little more deeply.
Yeah, so this is based on a journal article. It actually includes the pressurized water reactor with the conceptual. But this year, we'll actually undertaking a huge effort at Sandia to provide more mathematical rigor with real experimental data. So we'll be having those likely, probably June, July of this year.
Thanks for your presentation. I've got a question regarding the delineation to safety. So what parts of the UCAs are already covered by safety? What can you draw from safety, and what is beyond that and the security?
Yeah, so for instance, like NuScale is an advanced reactor that are licensed by the NRC. They have a full STPA analysis on safety. So they're always looking at what are the control actions that would lead to what they call licensing basis events, right? So licensing basis events are those events and sequences within the failure modes and effects that lead to essentially loss of any one of your 3 safety functions. And so the example I had was the steam generator tube rupture. That would be one of the ways that the STPA would be used, along with what they call probabilistic risk assessment, to take it from the steam generator tube rupture to those events that are meant to be totally unacceptable by regulation.
Okay, thanks.
No problem.
Yeah, it's clearly you've done a lot of thinking about this and how it applies to nuclear. I'm wondering if is there anything that's unique about the nuclear sector and the way that you guys approach safety, security, and engineering that would make it a challenge to adapt in other sectors?
So this is completely agnostic of the OT domain, other than you have to have an STPA analysis, right? So you can do STPA analysis. I've seen them on electric cars, vehicles. I did that for my thesis, actually, was one on the battery control system. There's also ones within like hydroelectric. So anything that you can perform an STPA analysis, even the Challenger disaster, you can apply this approach, right? We only focus on nuclear power because we're able to validate, right? With the Ashira, it's a pressurized water reactor, so we're able to validate our assumptions using experimental approaches. So it gives us a lot more rigor in the research rather than just sort of provide conceptual examples. Okay. Well, that's it for the questions. Thank you very much. It was a pleasure to be here with you.